Hello everyone. In this video, I'm going to ultimately show you what we're looking at here in Rhino, which is this shape I've made here, which I'm going to claim right now, at least, is actually perfectly symmetrical about a reflection. Now, obviously, if you just use your standard definitions of that, that is not the case. But I want to show you how sometimes I can take things too far and really dive into the idea of geometry as a way of understanding patterns to create something new. And so it's going to take several steps to get back to this Rhino file, because I just want to walk you through sort of the history. In other videos I have posted, I talk about why patterns are important, what the basic concepts of pattern and symmetries are, and how that relates to beauty and into architecture. And this is just a purely theoretical study just to show how you can take simple ideas like are really represented in some of the other videos and make them really complex, again, maybe too complex. The first thing I want to jump to is this file here, which I made when I was an undergrad many years ago. I think probably this was in the 90s, and we had to do this little campus project. And so I was already starting to think about geometries and symmetry and what symmetry meant in terms of beauty. And I was realizing, well, why, in buildings, we often talk about this vertical axis of symmetry only. And that deals with gravity. Like there's a reason why we deal with this vertical axis, because that's, we need the solid earth and buildings reach up to the sky and all these things. But I sort of said, okay, well, in other things that we consider beautiful, that axis can really be anywhere. And so I said, okay, well, maybe we rotate the axis. What does that produce? What if we don't have symmetry? What if we have one? Maybe the axis could be horizontal right along here. Maybe there's two pieces with each with their own symmetry, or three pieces, and so on and so forth. So I just started exploring the idea that the axis can be something to really be studied in architecture and in symmetry. And it's very base, and it worked great for this project because it could create buildings that sort of were similar really quick to create this sort of campus plan, as I had to do sort of in that project. Um, okay, one thing that you may or may not know is that actually two mirrors equal one rotation. And there's some things that I think can spring out of this in the studies that I was doing. And so here we go. I got this crazy shape here just for simplifying what that is. And if I mirror it against a vertical axis, it becomes this, pretty easy to understand. And if I take this shape and mirror it against the horizontal axis, it becomes this shape, right? So this shape is that shape with just two mirrors, right? I could have done that more easily. I could have taken the same shape. This shape here is the same as this shape here. And if I just rotate it, it becomes this shape, right? And this shape is that shape. You can see it, right? So two reflections equals one rotation. When I sort of realized that two mirrors equal one rotation, I said, oh, maybe there's something similar here. If I think about it, maybe there can be some clues into how this all works. And what it turned out to be is it's a relationship of this to the axis, right? So sort of similar to how I was thinking about different axes earlier in that earlier work. The reality is the difference between reflection or mirror and rotation is just about how the axis relates to the plane of the object you're drawing on. So in mirror, the axis is in the plane that you're drawing on, right? And then here, this and this shape are just symmetrical, 180 degrees rotated about that axis. That's a flip. It's a rotation. We don't think of it as a rotation. We think of a mirror, but I can have an axis. I rotate it over. That's what you get. When we think of the word more traditionally of rotation, we think that there is an axis. We don't usually think of it as much of an axis, but it's because it's perpendicular to the plane we're working with. So we can see here, if I have this axis here and rotate 180 degrees, I've just rotated that object around. So really, these two concepts are very similarly related. It's all, again, about the axis. And so I started to say, okay, well, there some interesting things to do if it really is about axis and rotation? That's fundamentally what symmetry, mirror, and rotation is about, axis and rotation only. What are some fun things we can do with that? How can we start to exploit this? So one easy thing to do is, okay, well, here's traditionally what a mirror would be. Rotated 180 degrees in the plane, you get this mirrored object. But why rotate it 180 degrees, right? Why not like 90 degrees or any angle, but 90 makes sense for buildings. And so I have this picture here of a house I did not design, which each elevation in itself is not symmetrical at all. But in the way you really look at it in the real world, sort of approaching from this corner, it is a symmetrical building. So essentially it is this concept of mirrored only, in a three-dimensional space rather than two-dimensional space, and only doing it 90 degrees. And so once you sort of break that down and start to do this, I can go, and this, sorry if this gets a little wonky or over the top, but it'll get to those drawings that I showed at the beginning, and it helps explain, because if you're going to create these, you can break them down further into mathematical pieces. And essentially what that building is that rotation and reflection, they both have axes, they both have symmetries, and they're just a collection of points. Now, how do those points relate to each other is how I defined that rhino shape using grasshopper. And so the axes may be parallel or perpendicular to the plane. That's what I was saying before. The rotating a point the same number of degrees, that's important to it, whether it's 90 or 180 or whatever the case might be. So we can see like point 1A and point 1B, they're equal distance from a 90-degree rotation. Could have been 180 degrees or really any angle. And then point 2, which is over here, is the same thing, right? So it's a different length, but this length is equal to that length, just like this length is equal to this length, and the angles are the same in that case. So the distance from the axis, of course, will vary across points. That's what that last point is. But I sort of asked myself, what would happen if I did some crazy things like, what if I had a curved axis? I mean, I know a curved axis isn't a real thing, but I said I could make this line. If I didn't make this line straight, I could make it curved, and I could apply the same rules. I could say length 1A is equal to 1B and have a consistent angle, and length 2A be consistent to 2B about a curve rather than a straight line, right? And then similarly, what if the axis itself were also angled in not just a two-dimensional plane, but a three-dimensional plane? So I started drawing this up in CAD, and I just put this in here. And basically, this is what this is. This is fundamentally what that Rhino file is based off of, as you can see. And I just drew one line, I drew a second line, the most simple version I could do it, and then I drew a line between and extended it out and created a spline in between. So we can see this line is related to this line, is related to this line, because these little horizontals are all equally spaced on each side. Now, I do find if I take out the center axis, it looks weird. It's sort of a weirder shape. But when the axis is in, it starts to become sort of an interesting look. And I think that's key, because I think even though this is non-traditional symmetry, it the human mind can sort of interpret it. They realize that there's a relationship between those three lines. You might not be able to put your finger on it. If I didn't show you this, you wouldn't be able to put your finger on it, but you can visually see it and you feel it, and it makes it look interesting. And so this object is perfectly symmetrical. It's just that it has a curved axis, not a straight axis. And I sort of realized, I mean, this was not even intentional necessarily. I think it came out real interesting, though, is when I sort of drew the shape early on, I realized that it had sort of some reference to shapes in Frank Gehry's work, like this. Here's the Guggenheim Bilbao, in particular, this shape. But these sorts of relating curves relate to each other. And I'm not saying Frank Gehry worked in this way. In fact, we know he didn't. That's not how he works. It's just a way of understanding how he sort of emotionally responds to form and shape might actually tie back to the theory of pattern and symmetry I'm talking about. So even his work can be described in this way. So once I got sort of this basic CAD work done, though, it was like, CAD is two-dimensional primarily. I mean, I know it can be three-dimensional, but you use it two-dimensionally, and it's not, I had to draw each line manually. It was just a test, but I knew it was time ultimately going to go into Rhino and use Grasshopper and be able to really play with these things. So now I'm going to take you back to that file. So just as a quick peek, you can see this is my Grasshopper file here. There's actually more here. I'll be playing with this in here because there's things I can tweak as we look at this file, and I can actually make different connections, because they look at how you deal with those geometries. Like there's more than one way of putting all those axes, curved angles, and so on and so forth, 3 dimensions, all into different planes. Different ways of thinking about them to make them work at this level. And so these are different ways I can sort of connect and come up with different shapes. And I haven't done much with this architecturally, because it's still, I mean, I just made this summer as I'm posting this, so it's been like decades of thought to get to this point. But certainly now I've gotten this far, I could translate this into some building or some at least concept of a building at some point in time. But you can see fundamentally this is a lot like um, uh, what I was showing in CAD. In fact, if I turn off the Rhino work just for a second, you can see that the only thing, or sorry, turned off the Grasshopper work. The only thing I actually drew in Rhino was this curve and this curve. All right, and if I turn the whole system back on in Grasshopper, what it's doing is it's finding a third edge and then creating a surface between those three lines, right? And the way that it's doing it is it's starting by finding points that go horizontally across here. But again, that's so let me step back for a second because I think it was about to get confusing. I have a horizontal line here. It's the same horizontal line there. It's in 3 dimensions, as we can see in these various views, but they're all based on the same angle and same length from the midpoint, from this line, right? So this line and this line are the same length, and they're in the same angle 3 dimensionally to this point of the curved line, right? Of course, since it's curved, those angles change all the way through. Um, and that's the result. And now, since it is Rhino, in Grasshopper, I can come here and, of course, change the shapes in any way that I want to, and it'll all sort of change dynamically the whole shape. And that's just the plan, but it does work 3 dimensionally as well. So I can also, pull it up or pull it down and change it all 3 dimensionally. And it's sort of fun in this way. So now this line in the center here is getting a bit almost straight, so it almost looks symmetrical. So let me just, for purposes of playing, let me make that a little bit more curvy in shape and see what the result is. Now again, there is a lot of variations I have here. In fact, I have other files that are very similar to this that even do things slightly differently. But some of the things I can do in this file is I add more points. It just becomes more accurate the more lines I use, and the less lines I use, obviously, the less accurate it becomes. But that could be interesting as you go. So I have that ability. I've also, for fun, I've put in this too. So you can curve that surface around the third dimension. So that's like, am I mirrored 180 degrees or am I mirrored 90 degrees or anything in between, right? So that's sort of those base drawings I was showing in that presentation is that angle in 3 dimensions that I'm rotating about. That's what that allows you to do there. And I think for fun to highlight the fact, because again, I think it's really important that the axis be defined in these shapes. Without the axis, it just looks weird. And so one way of doing that 3 dimensionally is to literally offset it. And that's all I've done here. And that would, in the real world, I'm thinking that sort of creates a shadow line rather than having to actually draw that line itself out directly as I am when I sort of even it up here. What this file does is it's very similar. I just tweaked. You can see what it does is it changes, rather than being parallel, the lines being parallel to the x-axis perfectly, I can actually sort of fan them out so they're not parallel lines anymore. So that produces a similar but slightly different shape. But in theory, they're all angled. They're all the numbers are each individually for each of these base geometric lines are all based on the same concept. It's just where do they hit? How does they relate from one line to the other? So it's slightly more complex. Or I can angle them. Like there's no reason why they had to be parallel to the x-plane. I can angle them in any angle I want, right? As well. So that's what these two sort of factors. So I can fan out them from being parallel, and I can put them in any angle that I want against whatever plane I want. So all those factors can be played up. It's all based on those same rules to get sort of interesting shapes. There's other ways of doing it, like you could divide this line equally by a number of points and this line by an equal number of points. I have that file. It's a different one. I'm not going to open it because it produces very similar results. In that case, you don't have a fan or parallel lines here. You have whatever they happen to be, but then each individual line follows the same rules. It produces something similar. I like this file because it has more flexibility to it. There's more slide bars I can use in Grasshopper to change things up. I also have another file that does better for rotation, because rotation is similar, as I've said, but it deals with a perpendicular axis as the primary starting point rather than in plane. So again, it's very similar. It's just optimized for slightly different angles. So you can do sort of fun things like that. The point being is, like, you can come up with these crazy things. The point being, when you understand the geometry of what symmetry really is, I can call this symmetrical. All these lines symmetrical. Um, and these shapes symmetrical. And two, when you really get into it, you can take these simple rules and come up with creative things. This is not the only thing you can do. This is only an example to say, if you study these things and if you're interested, you can really take them quite far. Similarly, like the Frank Gehry example, maybe you don't want to be this nerdy about it, and that's okay too. And you can get through it just from feeling it out and just raw drawing or building or modeling or whatever the case might be. There's lots of methods to getting there, but they all come from the same base theory that beauty has a deep connection to pattern. And when we understand that, we can make great architecture. So keep making great drawings, everyone.